So let's walk through an example of doing a comparison here. So this is a table from your textbook of an example of doing a t-test of this kind, this case 2, where we're comparing two different measurements. Let's imagine we have an instrument that measures HCO3 minus bicarbonate in horse blood, because you need to know that for some reason. Maybe it's a way to measure possible doping in the horses or whatever. We have an original instrument, but we'd like to substitute it with something else that's either cheaper or faster to do measurements. So we have the means. The two different instruments measured the same sample of horse blood. And so we have the two different means, two different standard deviations, and how many measurements were done in each sample. And so to be able to compare these measurements, first we need to do an F-test. So we need to find the F-calc. So our larger standard deviation is here on the right. So we'll call this one S1 and this one S2. Okay, so we can write 0.47 squared divided by 0.28 squared, because F-calc is S1 squared divided by S2 squared. All right, and so let's go ahead and calculate this value here. I'll find my calculator. 0.47 squared divided by 0.28 squared gives us a value greater than 1, as it should, 2.82. Okay, now we need to find F-table. To find F-table, we're going to need to keep track of the number of measurements, because we didn't look at the table yet for this, but we need to know the values for the degrees of freedom. So we have 9 degrees of freedom for S2 and 3 degrees of freedom for S1. We'll need those to look up the proper F-table value. Okay, so let's go back to here. So this is what F-table looks like, the table. Okay, so different critical values of this. This is all at 95% confidence. We're going to use this for 95% confidence. Okay, you could recalculate this for any other probability you wanted, but we're going to stick with 95%. That's sort of our standard that we use in analytical chemistry. Okay, so we have S1 and 2. I forgot the values already, so let's go back to our whiteboard here. So S1 has 3 degrees of freedom, S2 has 9 degrees of freedom. Okay, so S1 has 3 degrees of freedom, or did I get those backwards? Yes, S1 has 3, S2 is 9, so our F-table is 3.86. Okay, so let's go ahead and write that down before I forget it. Okay, so is F-calc greater than F-table? No. F-calc is less than F-table. So that means these standard deviations agree with each other at 95% confidence. Okay, so that means we get to use the first equation that we wrote out to do this comparison. Okay, so now we do our t-test. So we need to write down t-calc. So went down too far, still need these results. So we need the absolute value of the difference of our two measurements here. So we have 36.14 minus 36.20 divided by the square root. Let me go back to the equation should be over here, up here. Divided by S pooled, which we'll need to calculate, and then this square root is over here. Square root of n1 times n2 divided by n1 plus n2. Now, what we define as 1 and 2 doesn't particularly matter in this case. For the F-calc, we need to keep the value larger than 1 because that's the convention, and that's how we'll look it up in the table. But we can call either 1, 1, and 2 here. It doesn't change the result. So we'll have 4 times 10 divided by 4 plus 10. So the thing we're just missing is we need our pooled standard deviation. All right, we can go back over to my notes over here. S pooled is this equation here. So S1 square root, whole thing, S1 squared times N1 minus 1 plus S2 squared times N2 minus 1 divided by N1 plus N2 minus 2. Let's write out that equation with the data that we have. S pooled is equal to the square root of S1, 0.28 squared times 10 minus 1 plus 0.47 squared times 4 minus 1. I've run out a little bit out of room on the right hand side, plus divided by 10 plus 4 minus 2. Okay, so let's go to our calculator here. So we have square root of 0.28 squared times 9 plus 0.47 squared times 3. And everything is within the square root, so we're going to need parentheses here on the top. Divided by 12 gives us a pooled standard deviation. We would expect something sort of in between our two standard deviations, and it is 0.337, so we'll call it 0.34. Okay, so that 0.34, as a reminder, goes here in the denominator. So we're going to need our calculator again to compute this Calc value here. So we have the absolute value of 36.14 minus 36.20 divided by our answer here, which is, where we can divide by 0.34 times the square root of 40 divided by 14. So our Calc is 0.298. Final step here is we need to compare Calc to T-table. Now the fact that this is small means likely these agree with each other. The smaller Calc is, the more likely Calc will be less than T-table. And again, our total degrees of freedom is we have 12 degrees of freedom. For 95% confidence, let's go back to our slideshow here. Here's T-table. 12 is not listed on here, but we can sort of, we can get it exactly from Excel, or we can say, well, it's going to be somewhere between these two values. So maybe it's about 2.2, something like that. And if we come back here, if it was closer, it would matter, but in this case, it doesn't particularly matter that if we have it exactly. So 2.2, we know that 0.298 is less than 2.2, so the results agree with each other. Now, let's go back and look at the original data to see, to make sure that makes sense. These values are very close to each other, 36.14, 36.20. So it seems very likely that they would agree with each other, and especially when you consider the difference in the values is smaller than either standard deviation. It's no surprise that Calc is quite small in this case. It's about an order of magnitude smaller than T-table. So it's not even really in question that these agree with each other. But just wanted to walk through the exact steps that you would take. In class we'll go over an example using the other, where Fcalc is greater than Ftable. And also on your homework, you'll get a chance to practice with that as well.